next speaker, Anne Bernard-Mantel, from Toulouse, and she is going to talk about stripe patterns in uniaxial magnetics in films.
Thank you. Thanks, your organizer, for inviting me. And I'm very happy to present today to you my work, and I'm going to make actually an overview because I am, so as an experimentalist, I am working on observation of stripe patterns for the last 10 years, but I'm also very curious about modeling. So for the last 10 years, I've been working with the applied mathematician. So in this work, is done in joint collaboration with Cyril Muratov from Pisa University and Valery Slastikov from Bristol University. And so today I'm going to present to you my understanding about stripe patterns and that I obtain from observation, from modeling, and also from micromagnetic simulations. And I am going to focus only on straight stripe patterns and in uniaxial magnetics in films. So, but first I'm going to summarize a bit of the history of magnetic domains and domain walls. Because I'm going to show a lot of old images of stripe patterns. So, in the 19th century, there was already the idea that there must exist elementary magnets because you cannot isolate north and south pole in a magnet. If you cut it in pieces, it will make many north and south pole instead of separating these things. So there is also a phenomena of magnetic saturation. When you saturate a magnet, all these individual magnets are going to align, but when they align, it's over. And there is also the concept of elementary molecular current from amperes. So now we have a series of elementary magnets, and in the 20th century they started to look into how from this elementary magnet to get a bigger magnet, and there is the observation that the magnetization saturation is varying with temperature. And also, it was rapidly understood from the theoretical point of view that this magnet cannot be independent, otherwise it would lead to weak magnetism quantitatively. So, in 1907, Weiss developed a theory of strong molecular fields, and later Heisenberg came up with a quantum mechanical exchange theory. So, also in the 20th century, the notion of magnetic domains appears, and okay, today we are going to talk about these domains. So, experimentally, the first hints of the existence of these domain walls is the Bach-Rosen magnetic noise. So, you take a piece of iron with a coil around, and you amplify the current that is passing through the coil, and as the iron core gets magnetized, there is this noise which corresponds to domain walls moving and pinching that was heard. There is also the 60 and Tonk experiment where they could actually electrically measure the presence of such a wall on top of the magnet. And finally, this is one of the first magnetic images of magnetic micropatterns, which were obtained by putting some magnetic particle on top of a bigger magnet. So from the point of view of theory, there is a theory of domain boundary propagation in 1929, and then the Bloch domain wall theory, but which doesn't take into account dipolar interaction. And finally, really the foundation of micromagnetism, including dipolar interaction. Okay, so this is the only slide where I am going to show something that is not only uniaxial out of plane ferromagnets. Okay, on the first row, However, the two first images are corresponding to cobalt, thin film seen from the top and from the side, and you see what we call decoration, which is also called branching. And this branching, you see it from the side of the sample. So this is closer to what I'm going to talk about today. And I just want to show another few more complicated images. So this is some weird thing you can obtain in iron. And here at the bottom, this is some very complicated thing you get when you have extra energy, such as strain that is usually present in presence of iron and silicium together. Okay, so it's just to show beautiful images. But now I'm going to focus exclusively on uniaxial ferromagnet. But before that, I want to talk about materials, because I'm going to show you stripe images coming from different material, and I want you to know what they are. So I have three categories of materials, and the first is the simplest, and my favorite is the ferromagnetic transition metal. So they are a part of the D-block Mendeleev table. They are ferromagnet, which means that there is only one direction for every atom, no matter. They could be an alloy of these, or they could be pure. And I just show some random examples. So this is a iron nickel meteorite, where what you see is iron rich, nickel rich and nickel poor phases. Nickel is a very nice material because it doesn't oxidize as badly as iron, so there is a passivation layer that forms and it remains very shiny. That's why they use it for coins. And here, this is a geological form of cobalt from which it is extracted, which is called smaltite. So this material, so when I talk about this material, they are not generally uniaxial, out of plane uniaxial. So here, only the cobalt can grow in this form, HTP form, which will make it uniaxial. Otherwise, it's not. My second theory of nice material in which we are going to observe stripes, this is also not naturally uniaxial, is a ferrimagnetic oxide. So these are much more complicated materials, and they are containing more than one sublattice with opposite magnetization direction. But okay, overall, they behave like a ferromagnet. If you don't play around with the temperature, at the end, what you see is going to be the resultant of the sum of these two sublattices. So I'm going to show images about spinels. So here an example is a magnetite. There is also a very famous type of material for stripe domain, which is iron garnets, among which the yttrium iron garnets. There are perovskites. So this one is not magnetic. Magnetic ones are more artificial. So this is a double perovskite. And okay, there is also this magnetoplombite. So all of these have unit cells that are awfully complicated, and they are not uniaxial, but they are made uniaxial by growing on special substrates. And the third type of material is a more recent and fashionable type of magnetic material, which is called van der Waals magnets. And this type of magnets, they can be exfoliated just like graphene. And so they exist in this form of multi-layers. And this is here high-resolution transition electron micrography images of such materials. And okay, you can also engineer their magnetic properties in order to get out-of-plane anisotrope. And now, so this is some stripe images in these different types of material. So we find here this ferromatic transition metal, and this is my favorite because it's just cobalt, and it can grow in this natural HCP form, which shows natural an out-of-plane anisotropy. Okay, the image is not very nice because it's actually these stripes are quite small. Their size is 200 nanometer, and so it's not too bad for 1971. And for magnetic images, this is done by transmission electron microscopy. And so this is a very beautiful example in a very simple material. So such stripes can be observed in these van der Waals magnets, which are made with out-of-plane anisotropy. This is also an example in perovskite and a garnet. So the question is, we want to understand these stripes. You see that they exist in very different sizes and periods, and as an experimentalist, you want to be able to predict this. So for this, we are going to switch to some modeling, and to model this system, we are going to consider infinite film and impose periodic boundary condition. So we define this flat two-dimensional torus, which is a square box of size length L, with periodic boundary condition, where L is macroscopically large, and we define the non-dimensional period. So here I'm presenting to you my micromagnetic dimensional energy. So I have 5-dimensional parameters: the layer thickness, the saturation magnetization, the exchange constant, the magnetocrystalline anisotropy, so this is my out-of-plane magnetocrystalline anisotropy, and interfacial Dialoshinsky-Mori interaction, which luckily Kirill already presented. And this is my dimensional energy, where I also subtract the monodomain state to renormalize it. And here I do not specify the stray field, but this stray field is solving the static Maxwell equation. So we are going to first non-dimensionalize this energy, and from now on I am only going to use these non-dimensional parameters. And the good thing is that we are actually reducing the number of parameters from 5 dimensional parameters down to only 3. And these 3 parameters are the effective thickness, which is the thickness divided by the exchange length defined here. I have the effective anisotropy Q, and I have the effective DMI constant here. My unit is expressed in, my energy is expressed in units of AD. And I attract your attention about this notation. So M perpendicular represents the component in plane, perpendicular to the easy axis, and M parallel is the out-of-plane component parallel to the easy axis. And now we are writing the non-dimensional energy, where we have this acute expression for the stray fields, where here we have inverse Laplacian operator whose action of 3-dimensional plane wave is defined as follow. And this here I want to start talking about volume and surface charges, which are a very important notion to understand this mysterious stray field effect, which are at the origin of the stabilization of the stripe pattern. And so the stray field energy represents the Coulombic repulsive energy of these magnetic charges, which are of 2 types. There are surface charges and volume charges related to the variation of the magnetization in the bulk. So I will talk a lot about these magnetic charges, but here I want to say that I'm going to talk about 2 types of walls, and so 2 types of stripes. And why is it so? It's because we are considering these two energy, which are the two energy which are favoring the non-collinear alignment and making the stripe pattern exist, because if there was only exchange and anisotropy, they would be just a ferromagnetic state, right? So the stray field alone is stabilizing the stripe, but here I'm also considering another energy term, which is the Dzieloszynski-Morier interaction, and this interaction is favoring a given chirality of rotation. It is strongly reducing the cost for a domain wall, but it is favoring Niel rotation. And this is enters into competition with the stray field energy. This also favors non-collinear alignment, but in a really non-trivial way. Question? Okay. So, but this favors the block wall rotation because it doesn't create volume charges. So these two are going to be in competition, but somehow we are not going to look into this competition. We are going to look at cases where we have this dominating or this only, and that's it. So we are going to show a first regime where the walls are sharp, and this is happening when the effective anisotropy is strong, and we conjecture that the global energy minimizer is this periodic array of sharp stripes. So if kappa is larger and of the same order of delta, then the wall has a Niel character, while if kappa is equal to 0, the wall has a block character, as I already said. And this is how now we can express our micromagnetic energies. And you see that we now simply have the local part which is proportional to the wall energy. And here the wall energy takes the form of anisotropy renormalized with a local stray field, which represents a cost, as I say, for Niel rotation due to the volume charges that are created, and the DMI, which is going to reduce this wall energy. While for the block case, we only have here the cost of the wall, which is a mix of anisotropy and exchange. The non-local part expressed the same. And we are going to work in what I call the Kaplan regime, because it was worked out in 1993 by Kaplan and Gehring, who used this and that, which is a step function, periodic. And we defined this energy of the stripe pattern as function of the scaling L, which is the period. And this is what is minimizing our energy. Okay, so here there is a lot of calculations to obtain the stray field energy in particular, because the wall part is relatively trivial. But so this, I don't go into the detail of this calculation. I give you directly the solution, but we are working in a regime where the thickness is much smaller than the period. And in this case, we obtain two formula for block and Niel rotation, and this expression of the energy density enables us to obtain analytical, explicit prediction of the stripe width, which was obtained by Kaplan, and Milev did an explicit prefactor, which was only calculated numerically by Kaplan. And in our case, we came up with same thing, but for the Niel case. So okay, you can see here the difference in the wall energy. So this is the first. So I'm very happy as an experimental physicist, because here I already have an explicit expression for the stripe width. But okay, things are not so simple, because this is just one regime of validity. So coming back and showing a little more about the computation of the stray field. So we have to compute this sum, and in fact, I told you already about this regime in which we obtain these two formula, but actually there is another regime which was already derived, which is the first actually theory of stripes that was derived in 1946 by Kittel, and in this regime the thickness is much larger than the stripe width. And what is happening is that somehow the surface charges, which are contributing in a way that they are reducing this alternation of surface charge is reducing the energy, they are calculated separately and they are non-interacting. While here, it's not so interesting anymore because they are starting to compensate each other also from the top and the bottom. So these are two different regimes now that we see, but okay, there is even simpler formula in this regime. So I can now plot all. So in fact, so this is just the simple way these things are expressed as function of thickness. So now I can plot the log of my period as function of log of the thickness, and this is how these two regimes appear. So here for small thickness compared to the period, large thickness compared to the period, and in between we can Cohen simply carried out numerical minimization, and you see that this numerical minimization enable to go between these two regimes. So now we already get a pretty nice picture of this. But and okay, and this is actually was already observed experimentally, this transition. So here you see in the case of this famous garnet, magnetic garnet, you see that for thick layers we are in this Kittel regime where the stripe period increase with the thickness, while when you get too thin, as I was saying, the surface charges start to cancel each other by proximity between the top and the bottom layer, and it becomes less and less favorable to form these stripes, which gives rise to a very fast increase of the period, so fast that it's hard to catch it experimentally, except if you are observing a sample which has its shape varying in the distance. So this is what we call a wedge shape. So, and this is what you can see here. This sample doesn't have a constant thickness, and by making a very fine wedge, they are able here to observe the variation of stripe and this exponential increase of the stripe width. So okay, so I'm starting to put things in a summary here. So far we have this already these two regimes. So things are already not so simple, but it turns out that there is yet another regime. And where does this regime come from? Well, there is these sharp stripes that I was talking about, and but it's not always the case. So we have to go beyond this approximation, and for that we have to look at another important characteristic, which is the width of the domain wall. How does this width, that I call W, and that have a different expression depending whether your film is thin or your film is thick. And this wall width, you have to compare it with the thickness to figure out whether your sharp stripe approximation is valid or not. And if not, you will have to do a more careful calculation of the long-range interaction of the wall, because they will start to play an important role in the energy. And it turns out that indeed, experimentally, there is two regimes where we see this exponential, very fast variation of a stripe width. Here, what I was showing you was happening at the micron scale, but in the 90s, when people started to be able to make wedges of a few monoatomic layers. And here there is you can see that the thickness of the iron layer is varied between 2.4 monolayer to 2.8 monolayer. And we see this very fast exponential increase. And this is happening in the nanometer range. So somehow we have this double exponential variation. And we also have to derive a model specific for that. And this was done by Kashuba et al., who came up with an analytical formula. And mathematically, there is also some work showing that there is such a scaling in the stripe width, which is proportional to the stripe width. Okay, however, so far there was missing the explicit prefactor. So as an experimentalist, I was unhappy because I need to know this alpha. And in fact, okay, it was not quite missing because it's here, but it was missing in the applied math work, and actually in the physics literature, it was calculated many times, but you can see that it was actually going all over the place. So my colleagues, they tackled this problem. So again, we can see the same micromagnetic non-dimensional energy. And now we are working in a regime which is this what we call the ultra-thin film regime, which means that the wall width is much smaller than the thickness. And the good thing is that in this regime there is a decoupling between volume and surface charges, and you see that the stray field energy appears in a local way here, renormalizing the anisotropy, and the non-local part of a surface and volume contribution. Okay, so from that we work again in these two regimes where we have a nail wall and block wall, and we are going to obtain these two Euler-Lagrange equations, and we are using the profile, which is for delta equals 0, is this. And from that we obtain again the leading order expression for the total energy density, so this very nice and simple function explicitly showing here in the front twice the whole energy divided by L, and the right hand side is the non-local part, which is so tricky to calculate. And here you obtain two new formula, again with this exponential variation as function of the thickness, and a brand new clean prefactor. Okay, so now I am going to, as an experimental physicist, to make a plot of this formula, compare it with the previous formula in the physics literature, and I'm doing this for a very concrete sample, which is a classical few nanometer thick transition metal with such a magnetic parameter. I vary its thickness, and here I show the block and nail case. Okay, so what do we do with that? Okay, so somehow we want to further convince my community that our model is the correct one, and for that I carried out micromagnetic simulations, which actually are very simple because you can carry out quasi-1D simulation. So this is a nail example, and we have a DMI which is strong enough not to have to worry about Z dependence, because we are going to, at some point, eventually crank up the thickness. And in fact, these simulations are very easy to make if you already know what is the equilibrium width, because otherwise you don't know what is the size that you have to choose for your system. So if you take a random set of my dimensional parameters, It could be that I'm looking for L, which is kilometric, and I still need to resolve my wall. So if I don't have any analytical formula to guide me, these simulations are impossible to do. But okay, I have the chance to have it, so right away I have my system at the right side because I already know where should be the stripe equilibrium width, and what I am going to do is that I'm going to minimize this with periodic boundary condition to represent my stripe pattern, and I'm just going to minimize while shrinking the thing, and eventually I obtain a minimum of energy, which is represented zoomed here, and I can compare this with my nice formula of energy density as function of L, and actually the agreement is very, very good. So I can then vary the thickness of my simulation and follow the minimum, and at the end I get all these points corresponding to the minimum, which are of course falling into the formula that was calculated by a mathematician. So giving an answer for experimentally that this is the formula that should be used from now on. Okay, so here is a summary. So we have now this three regime, and okay, I call this regime PSM because we were the first to come up with the correct prefactor. It's a bit presumptuous, but okay. And now I can put together all these formula in a single graph. So I carry out 3 simulations for 3 different values of Q, and here I represent the shape of the wall, where you can see that there is a transition from this flat wall, which is called ultra-thin film regime, to the Kaplan-Kittel regime. So here there is 3 zones where there is a good agreement with this analytical model. So there is this ultra-thin film regime, there is a Kaplan regime, and there is a Kittel regime. And in between, so here you need to numerically resolve this stray field energy. But also, if somehow your wall turns out to have a shape which is in between, you actually cannot calculate exactly its stray field energy. So here you see that, okay, this formula are giving a rough idea about the width, but you have to do numerical experiment to have the exact width. Okay, so now I'm gonna show, to finish, I'm gonna show 2 extra things that is bringing us to the understanding of something that is going toward three-dimensionality. Because so far, everything can be described by a 2-dimensional pattern. And one thing is to take 2 of these layers to remain in this regime of ultra-thin film, but we are going to cut the exchange to give some freedom for the wall rotation to do whatever it wants. And we're going to see what it's going to do with the stray field. And so for that, we construct such a model in which each layer is thin. Also, the total thickness has to remain thin in such a way that if you look at a wall width, it will be much thinner than the total thickness of your multilayer. And then we enable Z variation by setting the exchange to 0. So it doesn't cost, from the point of view of exchange, to turn. So let's see what the mysterious stray field want to do with this situation. And so, so we have a magnetization that is constant in Z in each layer. And so we carry out a complicated asymptotic expansion of this volume and surface charges interaction kernel, which contains volume, 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 surface, surface, volume within each layer and in between each layer. But finally, we obtain a very satisfying result which is giving us, so again you see the local action of the stray fields. You find again for each layer this usual intra-layer volume non-local that cost some energy for the rotation, and intra-layer surface non-local that are at the origin of the creation of stripes. But there is an additional term which comes from the interaction of the surface and volume between layers. And if you look at this, you see that it has exactly the same expression as the DMI. So it is going to favor rotation between layers. And if this rotation is in such a way that M parallel is anti-parallel, here we are going to obtain twice this term. This is going to become +1, twice this term, and this is going to be equivalent to a DMI term, favoring the rotation with the opposite chirality in both layers. And this is also a local term, so this is a non-negligible effect. And so we apply this to the case of a bilayer, and in this case we can prove, so this was done for the case of skirmions, but this is the same idea if you have stripes or just a wall, that you have such a favoring configuration that is in fact reminiscent of flux closure that this stray field wants to obtain. So this is some sort of toy model where we recover flux closure, and here you can see two domain walls that are going to have this very chirality. I want to mention also that if you push the thickness beyond a certain quantity, which experimentally is of the order of maybe beyond 10 micron, you are going to, the system is going to find another way to cancel these surface charges, something else than just forming closer and closer domain, and this will start to ondulate and eventually form some branching. So this is an observation in a single material. You see a progressive increase of the thickness. The stripes start to ondulate and more. This is also what you see on a wedge. And if you keep increasing the thickness, you will see this surface decoration which correspond to forming of branches, and what the system is doing is cancelling the surface charges by sending them in the bulk. So here, in fact, in the bulk, the stripe remains like this, uncharged block wall, but at the surface, the wall becomes charges, and we observe this. So this is just to add something on my summary. And last thing, I want to mention that there is yet another regime, and you see that up to now we looked at Q close to 1 regime, or very high Q regime where the wall is very thin, but you can look at an opposite regime which is Q much smaller than 1. And in that case, another way to cancel the surface charges is simply to put the magnetization in plane at the surface. And if your anisotropy is low, it doesn't cost so much, so you can have such domain, and you see again this famous flux closure pattern. And this is happening when, in the regime where the thickness, the block width, and the period is of the same order. And mathematically, we cannot say a lot so far about this because it's a very complicated three-dimensional regime, apart from this toy multi-layer I was talking about. But okay, so we can carry out some experiment and simulation in this low Q regime. And so you can see here electron microscopy image, and we are actually interested by this regime because we are trying to observe stripes which are as small as possible, knowing that all these stripes, they will transform into what you can call bubbles, skyrmionic bubbles, skyrmion, depending whether there is DMI or not, depending on whether their topology is non-trivial or not. But if you have such a very fine period, you know that you can create very small skyrmions, so this is interesting for application. So that's why we are interested in this kind of material. So by lowering the anisotropy, we are trying to see how small we can make this structure. But we also have to crank up the thickness. And it turns out that, okay, what you cannot really see here, in fact, here what you see is only the block component of the rotation. So it shows you only what's happening in the middle of the layer. But you can see here a nice three-dimensional micromagnetic simulation of this very case. And you can see here that I observe this flux closure domain, and this is what is called a dense stripe. So I have a continuous rotation, so it's more like a sinusoidal pattern. Okay, so my summary is already ready here. And to finish, I just want to tell you what are the publications of us related to this presentation. So here, in the ultra-thin film regime, we have two papers, so one on single layer and one on multi-layer, which also describes the skyrmion interaction in a bilayer. We are currently preparing a paper which is talking about all these transitions and redoing all the formula that were derived in the past with modern notation, also taking into account the DMI. And as I was saying, this is a very interesting system that is currently studied, this low Q system. So I have a lot of experimental observation. Actually, why is this system interesting? It's because in the middle of the layer, you have this block rotation. And what I didn't say is that the Néel rotation induced by DMI is homochiral. But the block rotation favored by the stray field, it is degenerate. It can be in one direction or another. And this makes the system very interesting because your stripes, what you don't really think about is that these stripes, in their core, they can be like this or like that. So this is what you see here in this simulation. And this will have an impact on what you observe, which is not visible here, but can be visible. And also, you now can create this array of bubble or skyrmion with these two different types. And here you can see an image of such a very dense array where we have some very ordered thing, and we have these skyrmions which can be quantified at plus or minus 1 depending on the rotation of this block core. And in fact, here what you obtain is something close to artificial spinized system, but where we didn't have to do any patterning. I mean, the nature is creating this dense array, hexagonal compact array of skyrmions with these two types, and now we can study the physics of interaction between these two types of skyrmion. And we also observe some interesting phenomena related to this presence of two types of walls. So we observe some in-plane domains of magnetization, and this is because we are close to the in-plane to out-of-plane transition. So this work, I'm going to present it in more detail in our workshop happening in Pisa in October for those who will be there. Okay, I thank you for your attention.
Are there any questions?
Thank you for a very interesting talk. I have a question, a curiosity really. So most of your experiments were done on these ferromagnetic transition metals. However, your model of ultra-thin layer or multi-layer, it seems almost like perfect for this van der Waals systems that you have described. Is there?
Yeah, so it's a very interesting question. Actually, I had a slide about it, but I removed it. So, in fact, so these materials I was showing, they can be either monocrystalline or polycrystalline. And the stripes are observed in all the cases. And the disorder is not something that is going to be specific to polycrystalline, because usually these crystallites are smaller than the scale at which the walls are happening. So it is not true that if you take a polycrystalline film grown by sputtering, you are going to observe a very messy system, and that in an epitaxial system you are going to have something very clean. Because the system in which you observe something very clean is an epitaxial system which is thick. When you go to a very thin epitaxial system, you have a lot of disorders that reappear. So this is this few monolayer iron. And this is despite the fact that the system is supposed to be perfectly crystalline. But when you have only a few monolayer, there is a lot of disorder appearing because you control the crystallinity in the XY plane. But in the Z plane, unlike the van der Waals magnet where you can really put one layer, two layers, you are growing one monolayer, but there is always steps and islands. That's why you can tune in between one and two monolayer very finely. And this creates some disorder. And the van der Waals is also not so perfect because you have to deposit it on something, and this something is not necessarily clean, so there is also some large scale. But overall, it doesn't really affect the scaling. Actually, it is difficult to say, because here you saw I was only comparing micromatic simulation with model and never experiment with model, despite the fact that this is what I was supposed to do in the first place as an experimentalist. And why is it the case? It is because you don't know your micromatic parameter precisely enough to be able to say anything in comparing an analytical model with an experiment. In fact, the only thing you can do is to fit one and another. And it's really, you don't learn anything, neither from the experimental point of view, nor for the modeling point of view. It's only really the comparison of simulation and models that helps you to understand. So it could be that indeed this imperfection disorder you're talking about have an impact on the width. But that I cannot say it from the experiment, because I can never say if my model is good by comparing it with the experiment. What you would have to do is to carry out simulation with disorder.